Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be talking about solubility and precipitation. So a little bit of this will be a review, but we're going to start extending this into some new fun systems, namely ionic ones. So when we're looking at the solubility of a solid, really what we're trying to often determine is how much of it will dissolve in a given solvent. Most common solvent we're going to typically be looking at is going to be water. And so if we're looking at a non-electrolytic solvent, so something that doesn't break into pieces, we can give this in the general equation form of solid goes to aqueous species. And that's more or less what happens. So if I'm looking at how well table sugar dissolves, that's in the form of sucrose, which is called a disaccharide because it's made of two simpler sugars. It pairs together and it will dissolve fairly readily in water with an equilibrium constant of 6, which I know doesn't seem very large, but it means that more of the solid, you're going to get a fairly high concentration of the solid to dissolve into an aqueous solution. And so anybody who's made rock candy will know just how much sugar is put in there before it starts precipitating back out. And so generally when we're constructing these equilibrium equations, one of the things that we really care about is the likelihood of the system either dissolving or forming a solid. And we can go ahead and figure this out by looking at the level of saturation of the solution. And as a quick review, we can do this using the equilibrium constant, the reaction quotient. So the equilibrium constant tells you exactly how much of the dissolved species is present in water at equilibrium, so at essentially a saturation level. However, the reaction quotient tells you how much of my products and reactants are going to be there at a given moment in time. So if our Q is larger than our K, it means that we have way too much dissolved products, because again, products over reactants, and this is called a supersaturated solution. I have too much of my dissolved species in solution, and it will tend to go to the left and form a solid. Conversely, if our Q is fairly small, it means we don't have enough of our solute in solution, and so we need to end up generating more of it. So any sort of solid that you have will end up dissolving to essentially increase the concentration of, in this case, sugar in the water. So in this case, we're going to find solids will tend to dissolve. Then we often have that nice happy intermediate where Q is equal to K. So this means that the amount of sugar in solution is the exact amount that I want, and and the system essentially won't end up dissolving more or precipitating out. It will just kind of stay as it is. And we've seen this before for essentially these non-electrolytic solutions. But what happens if I'm working with something that's electrolytic or breaks into ions? So in the case of these ionic species, we often write this as, say, sodium chloride solid goes to sodium chloride aqueous. Okay, that looks okay. Unfortunately, in practice, these ions won't actually stay paired together, and they will form two separate species, and they can actually possess independent concentrations. So for example, if I have a solution, if I'm adding sodium chloride to a solution that already contains potassium chloride, well, that chloride is already there, so the sodium and the chloride concentrations won't be equivalent. And this means that I need to try and treat each of these species as separate, the solid, the sodium, and the chloride all individually. And we can do this using what are referred to as solubility products, or KSP values. And so KSP is going to be a very good metric of determining whether or not a solid will form. So for the case of sodium chloride, this means my KSP is literally the concentration of sodium times the concentration of chloride. And it turns out that it is a KSP of 38. So yeah, this is quite a large KSP, which makes sense because we know that table salt, sodium chloride, readily dissolves in water. So it won't be a big issue there. And again, large KSPs like this means that we're going to have lots of product species dissolved in water at equilibrium. However, it turns out that not everybody is quite as simple as sodium chloride. We often have to watch out for stoichiometry that can play a role in these solubility products. So while my reactant is always going to be solids, so I don't have to worry about a denominator, we can have things where things get a little bit fun, like I've got calcium carbonate. Now my calcium and carbonate are both have a charge of 2, but I still have this nice 1-to-1 stoichiometry. And so my KSP looks pretty good, fairly similar to what I had. And calcium carbonate this is going to be a reaction we'll see a lot, because it turns out calcium carbonate is present in limestone, it's present in cement, it's also present in the soap scum that forms on your in your bathroom tub. This can form whenever you have lots of calcium, which you get from hard water, and carbonate, which, well, just exists in the atmosphere. Then we can contrast this with, say, calcium fluoride. So this is present as the mineral fluorite, which is quite pretty. However, we readily just mine it and then throw it into our drinking water because it's one of our principal sources of fluoride to fluoridate the drinking water. So in this case, what we find is that the KSP is actually fairly similar. But it turns out that there is a principal difference here. Both have the calcium concentration, but because fluorite produces 2 fluoride ions, it will have a squared fluoride concentration, which, as we'll see later, will really enhance or change the amount of ambient fluoride present in the water. Because while limestone is considered fairly insoluble, fluoride is considered much more soluble, though still registered as an insoluble species. Then we have something like aluminum hydroxide. So this is commonly known as alumina. It's present in a lot of metal ores. It's also present in some antacids and in some desiccants, as it readily takes up water. So with aluminum hydroxide, this one gets really fun because it doesn't split into 2, 3, but 4 different ions, 1 aluminum and 3 hydroxides. And so again, this really complicates its equilibrium constant. And you'll notice that these will have some very important consequences. So one of the first things we can do with these solubility products is use them very similar to how we used our Ks for simple non-electrolytic solubilities, and just trying to determine whether or not a solution will form a precipitate. So what we can do is just take a look at our Q. If our Q is greater than our K, we're going to form a solid. If it's less than our K, then any solid present will generate an aqueous solution. So let's go ahead and take a nice common example. So hard water. So everyone in the Midwest complains about hard water. All that hard water means is that you have a lot of excess calcium present in your water supply. This often happens because you're getting water from limestone-rich deposits. Joy, oh joy. Now, if the water actually also contained a 1 millimolar concentration of carbonate, would I end up forming a calcium carbonate precipitate on all of my pipes and sinks? So first thing we're going to want to do is turn both of these from millimolar quantities to molar quantities. And yeah, you'll notice that both these values are fairly small. So you might say, no way, not a chance. Except for when we actually calculate our Q, it's 1.5 times 10 to the negative 6. Okay, this seems like a very small value. And then you take a look at your K. Oops, it turns out that our K is even smaller. So our Q is much, much bigger than our K. So we'll actually end up forming a lot of precipitate. And this is a very common feature. When you start exposing hard water to air, which brings into play a lot of CO2, which can turn to carbonate, you can generate a fair amount of precipitates. There's also other common ways you can generate hard water precipitates using different other anions. But in general, this is the sort of stuff we're looking at when we're looking about solubility and precipitation. So next time, we're going to go ahead and take a look at the inverse reaction. What happens if I throw a solid into water? How much of the solid would I expect to break apart? Until then, take care.